Okay. Great. So, folks, we're going to get started here. While I'm giving a few introductory remarks, I'd like you to call up AnyLogic so you have that ready to go. Specifically, we're going to be opening up the model that we built last time. That model has been uploaded to the Moodle site and should be readily available for any of you to download if you don't have it on your home folders there. So just as a recap, within the past two lectures, we've been talking about this third type of dynamic modeling within AnyLogic, a type of modeling that is somewhat confusingly known as discrete event simulation. Now, discrete event simulation, the name of it comes from the fact that it's dealing over time with a series of events that occur at however finely or coarsely they may occur over time. Those events occur. So we might have an individual comes into a facility for care. We might have a nurse that's assigned to the individual, heads to pick them up. The nurse brings that individual back to a particular room where he then examines the patient and conveys some treatment, and the patient's released. And it's going from event to event to event. Now, it turns out that that can be held up in contraposition to what goes on in system dynamics modeling, where we have a notion of continuous time, but where continuous time is playing out in time steps that are traditionally more fixed in length, although with more advanced integration techniques, you can have some variability. Generally speaking, they're of a size that's fairly bounded. In discrete event modeling, we have time that can leap forward for long periods if there's no event scheduled, and then can play out in very, very fine time steps if there are events scheduled in kind of a bursty way. And within discrete event simulation, we'll often, within the same model, have some processes that have to play out at a very quick level, and some that only occasionally need updating. Think about the spread of an outbreak of something like flu. There may be many months over the summer where there's very little activity. You can go 1 month at a time or coarser in terms of your understanding of the burden of flu. But then there's going to be other times, say in key points in the winter, where it may be spreading very quickly and you have to respond much more quickly to that spread. So in discrete event type approaches in general, this notion of handling discrete events, we have a schedule of events that play out over time. That schedule has some elements of it that are statically scheduled, that are scheduled known to exist ahead of time and just have to be handled, say, at regular intervals. And then we have some events that might be scheduled dynamically, such as through a message sent by one agent to another. So there'll be an event schedule. This is time here on the x-axis. And we'll have events that might occur in a kind of bursty fashion, and then there'll be periods of stasis, and then other events might occur. And the job of the discrete event schedule handler is to kind of go between these events, handle the events, schedule any new events that may be required, such as the next tick of a counter that is for reporting, or another event that's being sent. And basically, the scheduler will handle and broker the handling of each of these events over time. And it may advance time by leaps and bounds in some periods, go from over long periods of time where not much is happening, and then for other periods, we may have very, very dense outcomes. You know, there may be an earthquake, and we have to simulate things at a very fine level of seconds for a period, and then there'll be years between other geological events where time goes very quickly. So this is the general notion of handling discrete events. And I'd call it, discrete event scheduling or handling. And of the modeling types we've been talking about, this sort of discrete event scheduling has been a characteristic of two of them. A characteristic of agent-based modeling and a characteristic of what is called, confusingly, discrete event simulation, DES. But what I'm highlighting is the fact that discrete events are not unique to this discrete event simulation methodology that we've introduced the past two lectures. In fact, this notion of discrete event scheduling is in common with certain variants of agent-based modeling, which also are based around schedule handling. There's other types of agent-based modeling that actually make use of discrete time steps. You may remember one of those that we looked at. Does anyone remember? When we looked at, amongst our final lectures on agent-based modeling, we looked at a class of models where actually time goes in lockstep across an entire model in fixed ticks, as they're called, or steps. What type of modeling was that? What was a model we examined in that context? Anyone remember? It's about 4 lectures ago, 5 lectures ago. Game of Life was one of them. There was another one as well. Turns out, it wasn't Prisoner's Dilemma. It was the Schelling segregation model, where you had agents, and those agents could move from one location to another if they felt that their original location was not meeting their desire to be near people like them. They could move to areas where they thought people might be more like them, and out of that would emerge segregation patterns. Both of those were agent-based models which had fixed ticks for time. It wasn't continuous time at all. It was discrete. It leaped from time step to time step to time step, and conceptually all of the agents were updated at once for each step. Here, as in system dynamics, discrete event simulation, the methods we've been introducing, DES, as well as in discrete event scheduling, this kind of technical underpinning, we are dealing with a continuous time, as did system dynamics, also dealt with continuous time. In system dynamics, however, there's a continuous time abstraction, but we were typically integrating it numerically at a detailed level on time steps that in many cases were fixed using what's called Euler integration. And in some cases they vary using what's called Runge-Kutta integration, for example. You might have variable step sizes, but it wasn't based around a discrete event scheduling method. Here with agent-based modeling in continuous time and discrete event simulation as an approach, DES as an approach, or discrete event modeling as an approach, we have this sort of scheduling approach. Unfortunately, this whole area of modeling, discrete event simulation, discrete event modeling, has been termed that, even though it's not, discrete event scheduling is not unique to it. And it's something that causes quite a bit of confusion. You'll sometimes need to understand, are you talking about discrete event simulation as a particular modeling methodology, or are you talking more about the scheduling side of how the model's implemented? This issue of scheduling of events is an implementation issue that goes on behind the scenes. But there's also the whole modeling approach. Now, this modeling approach that we've introduced, as we've said in previous lectures, and I won't elaborate on it too much, is characterized by a number of features. It's characterized by defined workflows, and entities, where entities flow through those workflows, are operated upon by these processes. And the ability of those entities to be operated upon by a given process is dependent, on a typical level, on availability of resources. Give me a few types of resources we've talked about. What's one type of resource? Or give me an example of a resource that we've had in our model that governs their ability to proceed. A nurse, yeah, the availability of a nurse. Yeah, MRI machine, yeah. So these are two different sorts. One is static or fixed, MRI machine, an examination room, as we'll see. A particular robot on a floor of a assembly line or what have you. Fixed resource, doesn't move. By contrast, something like a nurse, a physician, might be a mobile resource. It can move around. And generally, the ability of a given entity to progress through this system is governed by the availability of these resources, right? And those resources are typically limited in their availability, so they come in defined amounts. And traditionally, they are defined in resource pools, where any given draw from that resource, any given thing in that resource pool, any given resource unit is interchangeable with another. So the idea is you'll come into the walk-in clinic on 8th Street, and you'll get served by a nurse or nurse's aide. You'll be served by a physician, but you're not all that interested there in who exactly you get served by. Similarly, you might take a taxi from here to the airport, and you're not all that caught up about which taxi it is. Is it taxi number 342 or taxi number 7044? You don't really care. What you need is a taxi. And so it is with these resource pools. You need a resource from that pool, whether it's MRI machine A or B, or whether it's nurse A, B, or C. It's not too important. So that's the general framework we're dealing with. If individuals are flowing through this system and their progress is blocked because a resource like a VQ scan here, or a CAT scan, or an ultrasound scan is not available, what happens to them? We saw it last time. What in general happens to them if a resource is not available? They wait. They wait in a queue. And by waiting, their time, their sojourn through the facility may be enlarged. And we're often interested here in key metrics where those things matter. So we're interested in throughput. We're interested in latency. So throughput, how many people per day are being treated, for example, by this facility. We're interested in latency, how long it takes a given individual to get through the system. We're interested in how long they're kept waiting. After all, they can't really blame the system if it takes longer because they're being treated along the way and they're receiving value. But if they're waiting, they might feel that their time is not well spent. We might be interested in the length of those wait lists. We might be interested in what fraction of the time are our resources in use? What fraction of the time are the nurses actually dealing with patients versus waiting in the lounge? What fraction of the time is an MRI machine in use? Maybe we'll purchase another if the usage of the existing one gets too high. We want to be able to do needed maintenance on it. So we're interested in these outcome measures. Now, a key thing that we haven't had time to discuss is the fact that there are, in many such cases, an interest in having in place mechanisms to look at the impact of movement and physical location of resources in different areas. And that's what we're going to be looking at today. We're going to be looking at giving homes for resources, define movement paths, and have entities interact with these resources in ways that require movement. Okay? So these entities are what flow through the system, and they're going to be operated upon by these processes. But at certain points, they may have to go certain places, and resources will be amongst the key reasons they have to go to those places. Okay. So we're going to be defining some flowcharts to top our system. Last time, these are going to be not linear in form. They're not in a mathematical sense, but in the sense that they split. or sometimes rejoin paths, and we're going to be defining resources here for it. We may come back to these slides, but in the meantime, I want to dive into the modeling. So a strange smell has descended upon the room. Does anyone else detect a sort of change in air quality? It's almost as if diesel is being pumped into this room by a tailpipe on a giant truck. Yeah, I share your concerns. And if it becomes, if it reaches too high a level, I will declare this a home exercise. And seriously, if anyone has asthma concerns or anything like that, I'd appreciate it. I consider this highly objectionable levels of air quality and a threat to occupational health and safety. And I will, in fact, place a call whilst on the recording here to complain. So, ladies and gentlemen, let's go open the model from last time. And we'll go reacquaint ourselves with it. So in this case, we confine ourselves to just to a single facility. Previously, we had actually seen a situation where we simulated multiple facilities located throughout a city. Here, we're confined to a single facility. Hi, Heather. So maybe you could call FMD. We're having absolutely horrible air quality over here in S320. It's like a tailpipe of a giant truck is pumping diesel. Yeah, S320, and yeah, it is a danger to occupational health and safety. If you could let them know. Yeah, exactly. Alternatively, if they want to provide gas masks, we'll consider that. Okay. Thanks. Yeah, if you could, thanks. Thanks a bunch. Bye-bye. Okay. So she speculates that there's a truck backed up against the air intake. And I agree that this is a plausible hypothesis. Okay, so ladies and gentlemen, here's a characterization of a single facility. We have individuals coming in. Right now, we have a pool of nurses. The size of that pool was dependent on the value of a parameter, which can be set for different particular simulations, different particular scenarios. So this is the capacity. Individuals, in order to be to undergo treatment within the facility, they have to be worked up by the nurse. And here, in order for that to happen, a nurse has to be assigned to them. By virtue of assigning them, they can undergo a process of workup, after which they're discharged. But if the nurse takes too long a time to be assigned to them, those individuals may elect to leave without being seen. In other words, to balk. Right now, we have a fixed timeout of 75 minutes, which means that if someone here waits too long, they may, beyond 75 minutes, they will leave. In general, in discrete event simulation, we will draw pretty heavily on stochastics during the simulation. And this fixed level of 75 would more commonly be characterized using a distribution. So we might say, well, some individuals are more impatient than others. Some individuals have more serious conditions than others. And so they're willing to wait longer, or someone who's more impatient will leave sooner. Okay, so this is our model. And a model like this had many virtues. We could change the availability of resources and examine the effects. We could examine effects on latency with these measures here. We could, in principle, look at utilization, which we did last time. Looked at utilization of this resource. We could also look at things such as throughput, people treated per day. And we actually had some measures of how many people have been treated and how many went via the bulking route versus this route here. But our query today, ladies and gentlemen, is different. Our query today focuses on physical locations within the facility, okay? And in order to address that, we're going to go to this palette here, and we're going to tap into, as we are wont, a different component of the palette. It's called space markup. Okay. Now, space markup actually is something which we briefly tapped into for GIS. We did draw a GIS map from there some time ago, a couple lectures ago. Today, we're going to be tapping other features of this. And we're going to go back and forth between this palette and this, this process modeling library here. So we are going to make use of these primitives here to characterize a given facility. And this facility is going to be one that we have a diagram for. And that diagram will allow us to sort of characterize the physical layout and, by extension, characterize the paths which people have to follow in order to move around the facility from one physical resource to another. In other words, to move from one important location to another. So we're going to engage in some artistry today to draw out said facility. Okay? So open main, go here, and I would like to drag in a rectangular node here, which is going to be called reception. Okay? So this rectangular node, different from the polygonal node, which is more involved. And this node will be called reception. Okay? Reception. Okay. Now, the reception that we're going to be laying out, I'm going to be drawing things with a certain size. It's actually not absolutely critical you have precisely the same sizes. So I don't want you to sweat the details of exactly how many pixels they are on the side. But the overall layout, we should try to capture in common, okay? So this is going to be a reception area for people to walk into the facility. We are subsequently going to have several additional smaller rooms, which will be separated by a corridor here. And I'll make the corridor of length 3. This is going to be an examination room where the workup will take place. Okay, so we will call this examination room 1. Okay, and next I will have a duplicate of this, and an easy way to do it is to select it, do copy and paste, and then use the keys to maneuver it into position. Alternatively, you could hold down the control key, maybe it's command on a Mac, and you could drag it and sort of deploy it. And I'm going to deploy 4 of these, okay? 4 of them down like that. And you'll notice there's a distressing kind of misplacement of one of those that I'm not sure, but I'm not going to worry about it. But if we had used the latter method, holding down control, dragging, and letting go, we could have avoided. By copying and pasting them, you'll notice that I have not coincidentally set their names to be appropriate. Examination room 1, 2, 3, 4. Make sure yours are named examination room 1, 2, 3, 4. Okay? Okay, these are going to represent rooms in which the workup undertaken by the nurse will take place. Okay? Next, we are going to set up, and I'm actually not sure if we will be requiring it within the time constraints today, but I'm going to set up over here, just beneath the this room here, an area that's called X-ray X-ray imaging. Okay, and finally, we will set up just down here, and extending over partway, we'll set up a nurses lounge. Okay, so that's an area where the nurses can be. They can store their personal effects there. They can take notes on patients, that sort of thing. Okay. That seems a little bit on the large side, so I'm going to shrink that. I don't want to suggest that nurses lead by any means a luxurious life. Okay, so here we go. So we've laid out here a facility, and a key thing is that each of these has some function, some role in life. And you notice there's a few of them, the examination rooms 1 through 4, that are kind of conceptually a pool of interchangeable rooms. They're, one could substitute for the other. It really doesn't matter for the service offered to you whether you're in room 1, 2, 3, or 4. Okay, this is going to align with our notion of a pool. Okay, ladies and gentlemen, so that's part of our work here. And again, don't get caught up in the exact details of this, but make sure you're using this from space markup. Next, we are going to drag in paths that will delineate travel conduits from one area to the other. Now, this part is a little bit persnickety, if I could use a term for it. And if I drag in the path here, you'll notice it enjoys a shape of convolutional note. And I want to actually pare this down. I'm not going to use highly curved shapes, perhaps because of my lack of artistic skill. So I'm going to actually pare this down to be a straight shape. And I'm going to do it by clicking on these handles to get rid of all but the first 2 handles. Alternatively, you can do it for all but the last 2. So if I double click on one of these handles, make sure you click on it. It will actually eliminate it. And now I get myself a rectilinear shape with which I enjoy more comfort. Okay. Now, this shape here, we are going to actually set. I'm going to copy this to be sort of replicated several times. But in order to do this quickly, it's best to make note of what I do. So I drew this shape. How did I do it? I dragged in the path, and I double-clicked on each of the little handles, so only the first 2 remain, so it's rectilinear. And I am going to go and set it to be not visible. By that, I mean that when I run the model, I don't want to see this path clearly, visibly. Okay. So that will allow me to then replicate it, and I'll get a bunch of other paths which will inherit that property. I won't have to worry about setting it for each of them. So, ladies and gentlemen, I am going to copy and paste this element. Okay. Alternatively, you can, come on, you can click on it, boom, control click, drag, and you can replicate it this way. And I'm going to engage in a very rapid replication of several of these things, just so I have at my material, I have at my disposal certain raw material that I'll be deploying to connect a couple different things here. Okay. So we'll need a couple of these different paths. And now, ladies and gentlemen, so I've just replicated them. All of them are not visible because I've copied and essentially just duplicated them. I don't want them to be visible at runtime. Next, and this is key, if I want said paths to connect resources, to be from one place to another, I can go and, and I need to connect it so on both sides it's green. Green is the color, ladies and gentlemen, and routing is the game. So we will drag this so it's connected on both sides, okay? So this provides a route to go from one node to another. Now, these paths will be interconnected, and it's going to take care of figuring out the shortest path from A to B. But in order for it to do it, it has to know they're connected and with what destinations they're connected. This is basically providing a path that's connected between these 2 destinations right now. We don't have to do it between all pairs. Rather, we just need a way of articulating paths such that they are interconnected, etc. So, ladies and gentlemen, here we have some pairs here, and I am going to go connect these up so that we have from each of these paths we can go here to a destination. Okay, here we go, and I am going to put in place a path as well to go, and it looks like I may need one more, so I'll just copy and paste here to get that one more. I'm going to go here into this juncture, okay? And I will do it from this to that. Now I'm a little bit distressed because I note that there doesn't seem to be an intersection here between the two. I would have expected this to sort of connect over. So what I'm going to do is I'm just going to sort of drag that to be to there, and then I'll make a copy of that and connect it over to here so that each point of intersection is clearly marked with kind of an indication that they are docked, that they have a point of intersection. So what have I done? I've defined a routing path, ladies and gentlemen, that ultimately connects any of these physical resources, the reception area in the upper left, the X-ray room in the lower left, each of the examination rooms vertically over here, and the X-ray area. It connects them together. And this routing area is composed of a set of segments which are docked at their final destinations, and which intersect with each other to allow for, say, an individual to come from here and be routed down to any of these other areas. And it will take care of all the shortest path logic and that sort of stuff. Okay? So this is our facility, ladies and gentlemen. We've laid out our facility, and naturally, if your mind is running ahead, you can realize that you could rearrange this facility. I could change the location of the nurse's lounge. I could change where patients come in and see its impact on the speed of processing and all that sort of stuff. Okay, so we've laid out our facility. Okay, make sure that these things are docked accordingly. So there's a little sort of points of intersection. Okay. My casual observation is that the air quality in our present facility is also on the rise. Okay, so ladies and gentlemen, next, what I'm going to do is I am going to add in. So I'll let you tell me what to do. So, ladies and gentlemen, I would like it so that we can reason about allocation of these rooms. The idea being, in order to be worked up by a nurse, not only does a patient need to be assigned to a nurse, they also logically need to be allocated a room. They need to be given a room in which to have the workup. How would I allocate something like that, a room, to an entity, a patient flowing through here? What sort of operator of these sort of operators in the palette for discrete event modeling, which we explored the last two times, what sort of operator would be associated with providing a given, say, a room to a given entity? Yeah, we need a resource pool. We need a resource pool, and then we need to do what to the resource pool? We need to seize it. We need to seize it. Okay? So, ladies and gentlemen, we're going to go to the palette, and we're going to drag in here a resource pool. And this resource pool is going to be called examination rooms. Okay? Examination rooms. Now, this resource pool will be different than other resource pool we defined. Because here, we need to associate it with what? We need to associate it with a well, physically mapped resource, okay, that is located at certain places, etc. So, ladies and gentlemen, we're going to go here and set the capacity is defined by a home location, okay, and it says based on attractors. I'm going to unclick that. Turns out we can use attractors to specify with greater precision exactly where things will live or what have you. So I'll just say it's defined by a home location. And you'll notice then we can specify the home location here, okay? And we're going to specify the home locations. What will these locations be? The examination rooms 1 through 4, okay? So we're going to specify that that's associated with this resource, okay? Its capacity is defined by these. So there's going to be, by extension, 4 of these examination rooms. And we're going to here say that, you'll notice there's this puzzling thing where it asks for the speed of the room. Okay? We're not interested in rooms that move. We're interested in rooms which are static. So we need to actually specify that the resource type is not mobile, it's not moving, but instead it's static. You know, this is the third one there, portable. Portable means it can be moved. It's like an ultrasound machine. It has no agency. It can't move on its own, but someone could move it, could attach it and move it. And that's the word of note. They could attach it and move it with them, okay? So this examination room is a static resource. These are static resources, okay? Here's our examination rooms. These rooms are going to serve as the location for the workups. Okay, next. We are going to go to nurses. And for nurses, we are going to lend them some knowledge of location as well. What do you, of all the resources that we've created, what things would be relevant for those nurses, do you think? Anyone? Yeah, okay, examination rooms will be needed. And it turns out we'll take care of that with the logic for how the patient is treated and flowing through the facility. But what else do nurses have associated with their life? A nurse's lounge, yeah. Okay, so ladies and gentlemen, if we go to the resource pool, you notice we can define a home location for them, okay? And we can provide a plus, and we could say, okay, the nurse's home location is the nurse's lounge. The nurses are associated with the nurse's lounge by default. And as we'll see, when we release a nurse, ladies and gentlemen, say up here in our flow, so I'm going up here to now the workflow, and when we release a nurse, you'll notice that we can say moving resources, of which the nurse certainly qualifies. Do we want them to stay where they are or return to their home location? And the answer is, ladies and gentlemen, return to their home location. So when they're freed up, when they're no longer allocated to a patient, they will repair to the nurse's lounge. Okay? Here we have defined for an we defined a new resource associated with examination rooms. It's a static resource. We defined its capacity by reference to physical locations associated with it. And then we took a pre-existing resource we already had defined, and we gave it a home location, and we noted that when nurses are released, they return to that home location, okay? But there's something else that I'd like to do. If we go to nurses here, you'll notice that nurses within this resource pool have a set of characteristics. And one of the characteristics is going to be highly germane for what we're going to be examining. And what characteristic is that? It lies just above my finger. Yes, ladies and gentlemen, the speed of those nurses. Here we have it set right now to 10 meters a second, which in my experience is, I've known efficient nurses, but that's beyond my experience. Maybe we'll set it to about a meter a second, maybe a little bit less, maybe 0.7, 0.8 meters per second, something like that. We'll set as the speed for a nurse. Okay, 0.8 meters per second. By the way, you'll notice down here there's things that we could really plumb into if we wanted to. We could specify the shifts for nurses. We could specify what the break policy is for nurses. At what points they're allowed to go take a break by their jurisdictional rules. And that could have a very material impact on the staffing. We can specify their capacity in terms of a schedule. We may have seen that earlier, but we could say, they're actually defined by a schedule, when they're on or off, or how many are on at a given time. There's all sorts of things we could go into more detail. We, in fact, don't have time to explore today or more broadly in the class, but which are very relevant for simulating a real facility, and very powerful indeed, and very concise in specifying what you want to capture. Okay, so ladies and gentlemen, we have these nurses. The nurses are associated with a home location. They're released, and they move with a certain speed. But there's something key that's still missing. If we want patients to be examined in those rooms, what do we have to do in order to make sure that patients are examined in those rooms? That each patient is examined in a room of their own. What do we have to do? What do we have to add? What's the operator? Yeah, we have to move them to the room as a key thing. So that's absolutely central, and that will involve a new operator. An operator, ladies and gentlemen, called move to. An operator that lies there above my other finger. But beyond that, what do we have to do? Even before we move them to their room, what do we have to do? We have to seize it. We have to allocate them their room. And for that, we will use the seize operator. Okay? So, ladies and gentlemen, in order to do so, we will need to add a bit of space here. Whoa, okay, that wasn't what I meant to do. Okay, I will go and go select, and I'm going to add this. I actually shouldn't have moved. Well, actually, yeah, no, that's good. Okay, happy. And maybe I'll do a little bit more space yet. Oh my gosh. Okay. Ladies and gentlemen. Boom, boom. Okay. So what we're going to do is we're going to add in two operators pursuant to the suggestions made there. The first operator will be an operator for seizing the room. Here we will call it assign room. It allocates the room to them. It allocates a room to the patient. Okay. This assign nurse allocated, you may remember, a nurse, one nurse. And here, for assign room, we are going to assign a resource set from a resource set examination rooms. Okay? We're going to assign them from an examination rooms. And we're going to seize just one of them. And none of these things are particularly relevant. We're not going to send that resource to them. The room will not migrate to them, nor will we attach them to the room. Okay. Next, for assign nurse, we will go back to that, and we will actually need to attach the nurse to the patient. After the nurse is assigned to the patient, the nurse will travel with the patient. So for assigned nurses, we actually do need to attach them. But more than that, we need to send them to that individual. Okay, we need them, the nurse, to go to them, to grab them, and to walk with them. That's the attach. They physically accompany them. They're sent to them, and then they physically accompany them on the stages of their subsequent journey until they are released. Next, or if they're detached from them. Okay, so you can do a resource detach at a later time if you wanted to. Okay, for assign room, we've assigned them an examination room. And next, we are going to go and have them do what to that room? We're going to have them, I heard it earlier, Paul mentioned it, move to it, yeah. So we need to move to, ladies and gentlemen, move to here. We have to put that operator in between here. So move to will be called move to examination, or move to room. Let's just say move to room. And I'm going to drag it down here so we can see it with greater clarity. Okay. So for move to, ladies and gentlemen, you'll notice that here the agent is moving to a room, or they're jumping to. We're going to use move to. For stakeholders, that's often interesting, but more to the point, we'll be able to capture how long it takes them to go to different facilities. So if we're considering facility layout, endogenizing travel time, capturing that as a function of where things are in the facility. It's an emergent property of the simulation rather than being hard-coded. How long it takes to go from A to B. It's a function of the layout of the facility and the speed of movement of the different people in a group, etc. We're going to capture that sort of movement along over space. The destination here, ladies and gentlemen, will be what? Do you want to guess? Is the destination a geographic place or a latitude, longitude? Is it a tractor or another agent? What is it? Seize resource unit, ladies and gentlemen. We're going to send them to the resource unit. And to what resource unit will we send them? Examination room, ladies and gentlemen. Okay? And they will move with a certain distance or speed. And here we have the option of setting that agent speed. We're going to not use that right now. Okay? We're going to see a different way to do that. Okay? Okay. So here we have them moving to the room. They're going to be worked up. They're going to be released here. And before they actually leave the facility or be counted as done, what also has to happen? Does anyone want to say? What also needs to happen? Yeah, okay. We're going to release, good. So release nurse should instead be release nurse and room. And in fact, what you'll see is that right now, it is defined as releasing all seized resources, okay, of any pool. It's going to release all the resources associated with it, to wit, the nurse and the procedure room. That's great. And the moving resources, the ones that are mobile, in this case the nurse, are going to return to their home location. But something else needs to happen to the patient, too. What has to happen to the patient before we count them as having left the facility? Yeah, they need to leave the room. In fact, they need to go back to the exit. Right? They need to return to the exit, ladies and gentlemen. Okay. So in order to capture this, this wasn't part of my, this particular detail wasn't part of my original plan, but we'll elaborate. So ladies and gentlemen, if we go down here to our plan, we're going to actually mark the exit from the facility, okay? So we will go and we'll go down to the space markup, and we will drag in here a point node. Okay. Okay. This point node is going to be called entrance and exit. Okay. Entrance, exit. And that's for the whole area. We can map it out in a more nice way. But fundamentally, this is where people are going to have to leave to. That's the destination to which they will have to leave. So here we go. I'm going to go, having added that point node in. By the way, I think we could have done it with an attractor as well. But yes, good afternoon. Hey, the fumes are less overpowering, and they've really gotten quite a bit better. Mm-hmm. Great. Yeah. 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 It's much improved. Much improved. Yeah. Yeah. But if they can watch their proximity to those vents, that would be good. Okay. Thanks so much. Much appreciated. By the way. Okay. So, ladies and gentlemen, here we will have move to exit as the move to. Move to, ladies and gentlemen, is for patients. Or is for the entities. It turns out there's a thing called resource send to, where we can send a resource to a certain place. For example, a nurse who has to go get a piece of equipment. She has to go get an ultrasound machine, a portable ultrasound, or we have to send the nurse to obtain some paperwork from a lounge, and so he has to go that direction. Okay, ladies and gentlemen, we're going to have move to exit. They will go to a certain GIS node, and it will be the entrance and exit for the facility. Okay, and at that point, we will record how long it's been that they've been in the facility, and their departure will take place forthwith. Okay, ladies and gentlemen, the time is nigh to run this model, but I'm going to go back to project, and I want to engage in one bit of frobbing activity before we run the model. Okay, particularly if you go to patients and you go to movement, you'll notice that here within each patient we can actually specify the movement for that patient. Okay, now you'll notice that I set nurses to be to have a rate that was all uniform, reflecting the fact that nurses to be on the job have to have a certain degree of physical aptitude for the job. Here, for the initial speed of the agent, we're going to have patients who have real mobility challenges, as well as patients who are able to travel rather quickly. And so there's going to be, in short, heterogeneity in patient profiles. So we're going to set their initial speed to be drawn from we'll draw a triangular distribution. Okay, this is a distribution with a certain central tendency. It looks something like this. It's going to extend from one point A to one point B, and it's going to have a maximum value at a certain point. And we will set it to be from 0.25. Perhaps this is a patient in with a walker who needs to proceed with due caution. To the maximum value will be 1.0, but the most likely value be something like 0.6, say 0.6, and then the highest value be 1.0. They have to travel with a nurse, so even even if the patient is a professor who enjoys a degree of rapid mobility, they're going to be slowed down by the presence of a nurse who may have to tote along clipboards and other things. So even said professor will be slowed within his trajectory through the facility. So here we have a triangular distribution. So here it's going to go, the minimum is going to be 0.25. There's going to be no probability of having less than that. The maximum is going to be 1.0, someone raring to go, but is ultimately going to be limited by the nurse, we know, and the maximum is going to be at 0.6. Okay? So a given patient will have a profile as given by this. By the way, you may wonder, why didn't I just use a normal distribution? That's a fair question. One reason that, that people within operations research do this sort of modeling, or any of the sorts of modeling, want to be cautious about normal distributions for something like speed is what? Can anyone tell me? A normal distribution. Why is it a little bit more involved to specify this as being drawn from a normal distribution if we want it to be meaningful? What's a characteristic of a normal distribution? Suppose I have a normal distribution that's centered at 0.6, and suppose it has a standard deviation, let's say, of 0.2. What's the downside of the normal distribution? Just drawing from that. Yes. And that's exactly it. That's exactly it. Bingo. Good job, man. Yeah, so it goes arbitrarily large on each side. Now, which of these two sides is it of particular concern that it extends arbitrarily large, that its support is infinite, as they'd say over in mathematics and statistics? On which side is it a big problem? The negative side. Yeah, I mean, on the upper side, you probably don't, it probably is fairly unrealistic to posit, small fractions of individuals who proceed at rocket-like speed through the facility. But the really big concern is that you may draw from a negative value, and a negative speed is of questionable. In this case, it'd be of questionable physical meaning to have a nurse traveling at negative or patient traveling at negative speed. The dynamics of that would be uncertain, to say the least. Okay, so ladies and gentlemen, we draw it from a triangular distribution, and there we can clearly set the minimum as well as the maximum within defined limits. Okay, so ladies and gentlemen, let us build this model. Oh, there is something that we haven't done. We haven't actually set them along this top path to go to the location. But there's actually one more thing that we need to. So I just built it, and it was a happy camper. But there's one more thing we have to do. What is that? What is another thing that needs to happen? If this is really the entry and exit to the facility, what other thing needs to happen? Well, they have to. Where do patients come in? How do we know they don't appear full blown within the nurse's lounge? So we need, at these sources here, we need to specify wherein they lie. And you notice that, fortunately, this is the thing that says location of arrival here, okay? And I'm just going to say they appear at a network GIS node, and it will, in fact, be the reception area. I'm not going to get into they come in exactly the exit, and then they proceed into the middle of it. I'm not too concerned, because typically they're kept waiting here anyway. I'm not too concerned if they appear at the exit needing to simulate their time in. That's not going to be typically added too much to their visit. And I'm going to have location of arrival for this one also be at the reception. Okay, here we are, reception, ladies and gentlemen. Reception. Okay. So I'm going to save this model so that we can distribute it with greater clarity of the name. I'd like to now go build it, make sure it's a happy camper. It builds complete successfully. And now I'd like you to simulate it. Okay, I'm simulating it right now first with a single nurse. And you'll notice patients coming in here. And you'll notice there's a certain amount of activity taking place. I'm going to slow it down a little bit because time is proceeding in hours rather quickly. So here we have a nurse with a patient. That nurse is spending time with patients predominantly within these within the context of these examination rooms. And if we look at it closely here, what you'll find is the nurse will in fact travel back and forth to this location or to retrieve a patient and bring them back. The time is such that it's hard to immediately see where they move here. I might end up sort of speeding up or essentially having the examination take less time so that we can see them move hither and yon with greater clarity. But here the nurse spends some time with the patient. The patient will be discharged. We'll go out here to the facility and they'll go retrieve another nurse. And in fact, the nurse between patients would return to her lounge, but that lounge currently is not being used. Why wasn't that nurse spending time in his lounge? Can anyone say? What is it about the lounge that it's currently empty? Why is it that lounge is empty? Yeah, they're all busy all the time. Okay, so let's go down and let's go to the 5 nurses here. Okay, we're gonna simulate. This is a scenario we defined before, and here you actually see some more activity. You actually can see a fair bit of nurse activity within the facility. The nurses are spending at least a little bit of time within the lounge here, but they're being quickly bound to a patient. You'll notice that they're coming up here, spending time with a patient, and waiting for the room. Why is that? Why are those nurses spending time here with the patient, and in fact being viewed as allocated, rather than spending the time in their lounge? What's going on logically? Let's go look at our diagram here. Why is it that the nurses are going and spending time with the patient rather than spending time in their lounge? They're at least transiently back in the lounge sometimes, but what's going on here first? Yeah, there's no exam room ready. So they get assigned to the nurse, and the nurse waits with them. And because they're assigned to the nurse is no longer at risk about leaving without being seen, but the nurse is waiting with them in the reception area, which is not common in my experience. The Mayo Clinic does have something similar. So you go into the Mayo Clinic, and they'll actually have a nurse or a nurse's aide who, when you come into the clinic, will be bound to you. Wherever you travel in the clinic, they'll travel with you so they can help facilitate your awareness of services, make sure you're getting the appropriate care in different areas. They serve a navigation role, as it's called. So it's not totally unrealistic, but here it's a little bit odd. So what can we do if we instead want to make sure that the person is assigned to a room before the nurse goes there? What can we do? Yeah. 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 Mumble. I'm actually not sure. Let's see if we can examine that in a few minutes. That'll be an interesting thing. So can they go at warp speed with them? Yeah. I suspect they do what they do. I suspect that both of them engage in warp drive and zip over. Okay, so what can we do if we wanted the room to be allocated before the nurse goes to them? So the nurse only goes once the room is allocated. Anyone? Yeah, change the ordering. Flip the two around. Let's see if we can. I have a feeling this will be harder to do than it would ideally be imagined. Yeah. Okay. So we need to do a bit of rewiring here, ladies and gentlemen. So we're going to need. Hey, come on. So we're going to need to take this guy. Oh man. Okay, so I guess we need to. Okay, this is engaging in truculent behavior. So let me just see if I can select that. Okay, move it over like that. Happy. And now one thing I can do is move this. Oh, come on. Okay, I wanted to get this. Okay. Okay, I will go this. Oh, man. Okay, I will go delete this guy. And now I will put this guy in here, and I think he'll be, nope, it's not smart enough to weld them in. Okay, boom. Okay, so now we're going to assign the room, and patients will balk if the room takes too long to go, or if the nurse as well. So we're going to actually have a second route from here to here. So if they're caught waiting at either place for 45 minutes. So here we will have for assigned room, we will have enable exit on timeout, and this will be 45 minutes. And same thing for this guy here. Oh, sorry. Oh, 75. So we'll say 75, sorry. 75 minutes in both cases. Maybe we should have the difference. So maybe we'll say 37. 37.5 for the first and 37.5 for the second. They're willing to wait a smaller amount of time before each is available. Okay. This is going to be interesting though. I'd have to think that through a little bit more about what's best for that. Okay, so here we have assigned room and assigned nurse. So let's go see the dynamics. What should we see different than last time? Anyone? Once again, I detect malodorous intrusion upon this room. So here, what's going on that's different? What's visibly different now? Well, the lounge is well utilized. Nurses within the lounge are coming here and are spending time in the lounge until the patient is ready to be assigned a room, in which case they'll go. And because we have 5 nurses and 4 rooms, we typically will have a nurse available. And you'll notice the nurse resource utilization is somewhere around 75%, a little bit lower. So here we have nurses here occasionally. There's multiple nurses because there's few patients. But in general, we're going to have the rooms in use. Now, there's more we could do. Right now, I'm noticing some aberrant behavior. I think a lot of it is because we have overlapped areas there, but there seems to be some spilling into the hallway as well. And if we really want to refine it, we could go put in these attractors, which would specify essentially places where individuals can wait with greater specificity, and that would allow us to have sort of locations which are more to our choosing. You notice right now it's coloring the locations where they wait within a given room, and one of them is right on the edge here. Believe attractors, if we could put in an attractor here, we could go and place the patients at very specific points within this room. So I'll place it there, and this allows us to enjoy greater precision about where in fact people are waiting. So you notice now we found someone there. We'll do this for each of the rooms. we'll put in attractors for each of them, which will allow us to specify more meaningful or more usual places for them to wait, perhaps where the seats are in the room, or other features which where the patient would lay, an examination table or what have you. So I've just placed those resources. I'm going to go now to run the simulation. Okay. So now we have patients and nurses going to more well-defined places here. And once again, we can see there's, at any one time, some nurses which are present within the lounge. At any one time, it's typically one because there's only 4 procedure rooms. Now, we could examine this further, and I'm just going to introduce one thing before we break here. What I'd like to introduce is a process whereby we will sometimes have patients who need an X-ray beyond this. So suppose a certain fraction of the time a patient requires an X-ray. In this case, we're going to have another branch. Suppose they're assigned to the nurse. She determines or he determines that they need to get an X-ray. We're going to put in a branch within the logic that will capture that. So here we're going to go, and we will drag this over here, and we are going to, in fact, we're going to add a fair bit here. So we'll go to the palette. You notice that within AnyLogic, there's several types of operators here. We're going to put into place one that involves what's called select, and this is basically a branch point. Requires X-ray. Is testing for that. If they require the X-ray, they're going to have to do what? What do you think is going to be different if they require the X-ray? Well, they're going to need to be assigned the X-ray. So this is going to come with a whole set of patterns of issues. So we're going to need to go down here, and we're going to need to add in a resource pool. This will be a resource pool for what? What am I adding a resource pool for? The X-ray machine. It's going to, or X-ray room, it's going to have a capacity of 1. Okay. It's going to be fixed, static. Its capacity is defined by a home location, and that home location is the X-ray imaging. Okay. They're going to need to allocate that. Okay. And here we are going to, in order to allocate it, what do we need? What do we need for them to allocate it? Yeah, we're going to need to seize them. Seize the X-ray machine. So this would be allocate X-ray. We're going to need to move them to the X-ray, right, after it's seized. So for allocate X-ray, sorry, I should have filled that in here. I'm just watching the time a bit. Allocate X-ray, what are we going to need to do here? What are we going to need to specify in allocate X-ray? Speak on, use. Louder yet. What are we going to need to do in an X-ray? If we're going to allocate an X-ray, what do we have to tell it for that operator? Yeah, you need the X-ray. You need to allocate the X-ray. Good. We will move to, after it's allocated, we will move to a network GIS node, namely the X-ray imaging. We will undergo a given weight in the X-ray imaging. What do we use for that? What sort of operator do we use for weighting? A what? Yeah, it's a delay, so it's a where's the delay? Delay. Here we go. Delay. Okay. Next, we will. So this is imaging taking place. Next, we will free up the X-ray after they're done with that, and oops, we should say, okay, when the imaging is taking place, how long it will be. We'll say that it's going to take 15 minutes here. So the delay time will be 15, not seconds, but minutes. Following that, what do we have to do? What do we have to do after that takes place? Yeah, release it. Good. So release X-ray. And then what? Then we can move them to their room for examination. So they'll be examined with the assistance of the X-ray images in digital form that came from that X-ray. So we release the X-ray. Now, release X-ray, what does it release? Is it all resources? Sorry? No, just the X-ray. Okay. So all resources, and we can specify seized, say, from a given pool. Yeah, we'll do it only from the X-ray pool. Alternatively, we could have said only the resources sieved in the allocate X-ray. Okay. And they'll move to the room. They'll be worked up in the normal process. Now, the final thing we have to specify here requires X, right? It's a certain probability. We'll give it a probability of 0.1. Okay. So 10% of the time, a given individual will require allocation to the X-ray. And for that, I'll bump it up a little bit more just to be interesting, say 0.2. Okay. Now, this is going to possibly form another bottleneck, right? Because now we could have multiple people waiting for the X-ray machine. And in order to be examined for whether they need an X-ray, they need a nurse already being allocated to them. So that nurse will then be kept waiting as well. So now we've got some interactions. Having 5 nurses no longer seems so crazy. We have some individuals who are sent to the X-ray machine here. Other cases of individuals who are just placed here. We see the X-ray is in use about 60% of the time, interestingly. Nurses are in use just under 80% of the time. The examination rooms, about 97% of the time, ladies and gentlemen. Okay. You could see there is some balking going on. About 60 people have balked. We have a time through the facility that we can capture the latency from start to finish, ignoring those who balked, who left without being seen, is about 1.6 hours. And so far, of the 100, I'll pause it here, about 175 people who have gone, oh my gosh. Okay, there's something wrong. What's wrong here? I was suspicious. Why is the X-ray in such heavy use? Yeah, there's clearly, this is backward. Requires X-ray. Select true with a specified probability. So here, this is, and I'd have to go look at this. I had thought the true was this way and false was this one, but I'm guessing that it's backwards. So I'm going to say 80% of the time they go this top one, 20% this one. I thought that was the meaning. We'd have to go look up this block. And in fact, AnyLogic does provide us, if we go look at these blocks here, it does provide output true is the top. Okay, so the top is true, and only 20% of the time that was being invoked. So here we are, and it's a minority of people who need X-rays now. X-ray is only in use about between 20 and 25% of the time. Of the 180 people that have gone through, only about 41 have required X-ray services. The nurse utilization is about 76%. Okay. So, ladies and gentlemen, here we've endogenized movement. I just want to spend a minute or two emphasizing this. Why is this interesting that we've endogenized movement? Because it brings up the possibility of leveraging the model to generate emergent behavior in terms of the times it takes for things. Models generate behavior from interacting complex systems, from coupled systems, that isn't always very easy to derive. Here we have a sort of a branch system with certain probabilities, different things happening, variability in patient speeds, how quickly different patients can travel that affect their movement through the facility. And we can capture that heterogeneity. We can capture, the different rates at which people can move, the differential needs of patients as to where they go in the facility. I'm going to drag an attractor into the X-ray too. And we can actually use the model, as you might hope, to tell us essentially how long people spend in the facility on average, what are the waiting times in the facility, to what degree are individuals in the facility balking. We can use the model to help us understand the latency of the throughput of the system. This is of considerable interest. And we can examine how those things are changed, how those outcome measures, latency, throughput, waiting list length, waiting list time, etc. We can examine how those are changed when we have a changed layout of the facility or changed speed of operation of certain points in the facility. If we had different accessibility for wheelchair-assisted individuals or for individuals with walkers so that they didn't have to walk as far, we could examine what the impact is on these grand measures of these various parts. And what's very notable about this sort of modeling, we've specified a fairly complex system in terms of dependencies and in terms of possibilities, in terms of heterogeneity, how many patients there are that go slowly as quickly, and actually described it in a way that requires writing very little custom code, that really makes use of these operators, which are in the AnyLogic palette, and allow us to specify with a real conciseness and expressiveness the dependencies between resources, in particular blocks, between the resources and the entities that they serve, etc. It's a very powerful type of modeling for characterizing, once again, to emphasize it, in my closing words on this subject for the set of lectures here. It's a very expressive, concise, powerful way of characterizing resource-limited, structured workflows which operate upon entities flowing through the systems and allow us to understand how emergent features having to do with things like waiting, like queue size, queue length, latency, throughput, how those depend on resource availability and placement. Discrete event modeling can, of course, be simulated within agent-based modeling. We could build an agent-based model to capture this, but we would have to put in an awful lot of logic to allocate resources and free them and reason about the interaction of placement of a resource and the need to travel to it. It would take us a lot longer to build this model. Models are learning tools, ladies and gentlemen, and a model like this allows us to really quickly iterate big decisions like what's the facility layout, how many resources we have, and get really quick answers, quick learning to our questions about these sort of processes. discrete event modeling, you could say at a certain level, it could be duplicated by agent-based modeling, but that's not the point. This class is all about choosing the right tool for the job. It's all about metalinguistic abstraction, choosing how to express a given modeling problem with the right language for that job. And this sort of modeling, discrete event modeling, is an exquisite tool for describing certain classes of problems. Next time, we're going to be moving on to some basic processes involving parameter variation experiments, examining the effects of stochastics, of changing our assumptions about models. We're going to be going on to look at things like calibration and a deeper understanding of state space. But all of those will apply to all three types of modeling we've explored thus far, to wit, system dynamics, agent-based modeling, and discrete event simulation. So thank you very much. Thank you for bearing with us through the smog that has beset our classroom. And today, in light of air quality impairments, I will be holding office hours within my office. Thank you very much. Yeah. Yeah, sure.
As you know that I use my patient-level data in SLCD in RDs in order to my project.
Yeah, yeah.
We need we need to install the AnyLogic on-site RDC. No?
Okay. Okay.
I already requested to install the RDC in the AnyLogic. AnyLogic and the RDC
Yes.
centers.
Yes. Yes. So this is the RDC on campus.
Yeah, RDC
Yeah.
campus in the library.
Yeah.
As RDC asked me about the terms and condition of the